So let us welcome in next lecture of MAT-201, that is integral calculus. So in this lecture we will start chapter number 7, that is integral transformation. So this is the last chapter of this course. So first in this lecture we will see on line integral, surface integral and a column integral. So what is definition? What is line integral? First we'll see the line integral. So let's suppose f bar be a vector valued function, that is f1 I bar plus f2 j bar plus f3 k bar, r bar that is equal to x I bar plus yj bar plus zk bar. So we'll write dr bar, that is dx I bar plus dyj bar plus dzk bar. So the integration, actually it is circulation integration along the curve C f bar dot dr bar. So f bar is a vector valued function, dr bar is again vector valued function. So that will be equal to we'll write integration along the curve C f1 dx. So f bar dot dr bar. So what is f bar dot dr bar? You will write f1 dx plus f2 dy plus f3 dz. Yeah. So it will be integration along the curve C f1 dx plus f2 dy plus f3 dz. Yeah. So if just a minute. Yeah. If x equal to xt, y equal to yt, and z equal to zt are the parametric equations of the curve, then we can write this line integral along the curve C f bar dot dr bar equal to that is integration from a to b. So that is f bar dot dr bar by dt into dt. And here, what is dr bar by dt? So we'll write it as dx by dt, dy by dt, and dz by dt k bar. Dr bar by dt will be equal to dx by dt I bar plus dy by dt j bar plus dz by dt k bar. So its dot product with f bar will be equal to that is integration from a to b f1 dx by dt plus f2 dy by dt plus f3 dz by dt. So here the integration along the curve C f bar dot dr bar is called the line integral along the curve C. So this is the line integral. Actually it is called circulation. So definition of circulation, the circulation of a continuous vector alert function f bar along the closed curve C is defined as the line integral, that is integration of f bar dot dr bar along the curve C. So it is called circulation. See, so here C is a closed curve, that is condition. So next there is definition of rotational vector point function. Vector point function a bar is said to be rotational in a region if its circulation along every closed curve in the region is zero, should be zero. That is integration of f bar dot dr bar along any closed curve C should be zero. So C is any arbitrary closed curve. Then in that case, the vector valued function f bar is called a rotational vector point function. So here C is any arbitrary closed curve in the region. So this is condition on C. So again there is one remark: the necessary and sufficient condition for continuous vector point function to be rotational in a simply connected region is that it's a gradient of scalar point function. It should be a gradient of some scalar point function. So this is condition for a rotational vector point function. So examples. So these are the illustrative examples for line integral. So first evaluate the line integral integral f bar dot dr bar along C curve C, where f bar is given by x y bar plus yz j bar plus zx k bar, and C is the curve. It is r bar equal to t I bar plus t square j bar plus t cube k bar. T varying from -1 to 1. So it is given. See, so here r bar is given in parametric form. So solution as r bar equal to, that is xi plus yj plus zk bar, and it is given in parametric form, that is r bar equal to ti bar plus t square j bar plus t cube k bar. So from that directly we'll get x equal to t, y equal to t square, and z equal to t cube. So now you'll write r bar as, that is yeah, it is given, and you'll write dr bar by dt, that is derivative of t, that is 1 with respect to t, that is I bar plus 2t j bar plus 3t square k bar. So this will be the value of dr bar by dt. So from that you'll write dr bar, that is I bar plus 2t j bar plus 3t square k bar into dt. Also we have given, that is a bar, that is xy bar plus yz j bar plus zx k bar, and you can put the values of x, y, and z. So since here you can write x is equal to t, y is equal to t square, and z is equal to t cube, or sorry, yeah, what is that? Yes, it is t cube. So putting these values, so you'll get a bar, that is t cube I bar plus t5 j bar plus t raised to 4 k bar. So from that you'll write your bar dot dr bar equal to, that is t cube plus 2t6 plus 3t6 dd, or it will be t cube plus 5t its power 6 dd. So let us integrate. So again, it is given that so t varies from -1 to 1. So what is the circulation? Hence the circulation f bar dot dr bar along curve C will be equal to integration from -1 to 1 t cube plus 5t its power 6 dt. So after integrating and putting upper and lower limits, the value of this line integral will be 10 upon 7. So this is the required value of the line integral. So second example, evaluate. So this is second illustrative example for line integral. Let us evaluate the integral yz dx plus zx plus 1 dy plus xy dz along the curve C, where C is any path from the points 100 to 214. So here you are given it in three coordinate system. So here C is a straight line. It is path from point 100 to 214, means it is straight line from point 100 to 214, and again using analytical geometry. So this is a symmetric equation of line. So using that you will get the line passing through 2 points, and its equation will be x minus 1 divided by 1 minus 2 equal to y minus 0 divided by 0 minus 1, and equal to z minus 0 divided by 0 minus 4. So equation of line passing through 2 points in symmetric form you can write. Yeah, or same equation you can write in simplified form. It will be x minus 1 divided by 1 equal to y upon 1 equal to z upon 4, and you can write this equal value as t. So from that you will write x as 1 plus t, y as just t, and z equal to generally 4 times t. You can write this equation as suppose equation number 4. So it also gives that at 100 t equal to 0. So if x equal to 0, y, yeah, x equal to 1, y equal to 0, and z equal to 0. So what is value of t? So for x equal to 1, t will be 0, or y equal to 0, t will be 0, or for z equal to 0, t will be 0. And at 214 means if x equal to 2, then what is t? So t will be 1, or y equal to 1, t will be 1, or z equal to 4, again t will be 1. So you'll get at 100 the value of t equal to 0, and at 214 the value of t equal to 1, means t varies from 0 to 1. So from given, it is given that the value of this circulation, that is integration or C along C of f bar or dr bar, will be integration along C yz dx. So we are putting f bar or dr bar is yz dx plus zx plus 1 dy plus xy dz, and you'll write it as, so let us put x, value of x, y, and z. Yeah, so putting values of x, y, and z, you will get integration from 0 to 1 4t square plus 4t square plus 4t plus 1 plus t square plus t dt. So let us simplify this and let us put upper and lower limits. So we'll find the value of this line integral as 13.2. So again I will give two examples as homework on this topic, line integral. So this is about line integral. So next we'll see surface integral. So before that there is one definition, that is the definition of smooth surface. A surface R bar a bar UV is called smooth if a bar UV possesses continuous first order partial derivatives. So all its yeah, first order partial derivatives should be continuous. So when we say surface R bar equal to a bar UV is a smooth surface if its first order partial derivatives should be continuous. So next surface integral. So integral evaluated over surface is called surface integral. Simply, what is surface integral? Integral evaluated over surface is called surface integral. So let us see the different forms of surface integral. So let a bar R bar be a continuous vector point function, and let R bar equal to a bar UV be a smooth surface. Then the normal surface integral of a bar R bar over surface S is given by, that is integral or S surface S f bar r bar d bar equal to, that is integral over surface S, that is f bar r bar dot n cap ds. Here n cap is a unit normal vector, and unit normal vector to the surface ds. D bar is the vector area of an element ds. So it is there. So next it is definition of flux. The normal surface integral, that is a surface integral over surface S f bar dot d bar of a continuous vector point function f bar over closed surface S is called the flux of the F across S. So like circulation which we have seen for a line integral, so here the surface integral is called flux over closed surface S, and here f bar should be continuous vector point function. So what is a solenoidal vector point function? A vector point function is said to be solenoidal in a region if its flux across every closed surface in the region is to be zero. So again, like a rotational vector point function, here it is a solenoidal. If its flux is zero, then it is called solenoidal vector point function. So there is another form of surface integral, that is coordinate form. Yeah. So what is surface integral or yes surface yes f bar dot dr. So this is definition which can be written as integral over surface yes f bar dot n cap ds, and it is a surface, yeah, it is integral. So it is double integral over surface yes. So f1 xyz dy dz plus f2 xyz dz dx plus f3 xyz dx dy. So again, you can write it as, that is it is a double integral f1 dou y by dou uv plus f2 dou z by dou zx by dou uv plus f3 dou xy by dou uv. So here, what is dou y z by dou uv? It is dou y by dou u. It is a determinant of this matrix. It is 2 cross 2 matrix. It is what is dou yz by dou v? It is dou y by dou u, dou y by dou v, dou z by dou u, and dou z by dou v. So it's a determinant. And similarly, you can write for this too. Likewise. So again, we'll solve some illustrative examples on surface integral. So first, evaluate on the surface integral r bar divided by r cube dot dr bar dr over a surface S. So here surface S denotes the sphere of radius a with a center at origin. So note that. So what is r? R, that is yeah, it is magnitude of r bar. So at any point of S, so what is n cap? So n cap is which is a unit normal vector, and you write that unit normal vector as r bar divided by its magnitude. So for the normal, lies along the line joining the center of the points. So here, what is our required flux or surface integral? That is integral over surface S r bar divided by r dot dA bar, or it will be integration over surface S r bar divided by r cube dot. So what I'm writing, yeah, it will be r bar divided by r ds. Yes. Or you'll write it as, so after simplification it will be r bar dot r bar divided by r raised to 4 ds, or again r bar dot r bar, that is r square, and divided by r raised to 4, or it will be 1 upon r square ds. So here, what is r? So r is a, that is radius of the sphere. So it will be 1 upon a square, and it is integration of ds over s, that is surface area of sphere. So this integration is nothing but surface area of sphere, and which is already we know that is 4 pi a square. So 1 upon a square into 4 pi a square, so this a square will be cancelled, and that is 4 pi. So 4 pi will be the required surface area of the given surface. So second example, evaluate the surface integral. It is given, that is surface integral over S yz I bar plus zxj bar plus xyk bar dot dr bar, where S is the surface of the sphere, x square plus y square plus z square equal to 1 in the first octant, and you can do this problem as a homework. So next, there is volume integral. So let's suppose f bar r bar be a continuous vector point function, and v be a region enclosed by surface. This is yeah, smooth surface. That is r bar equal to f u v. Then what is the volume integral? So integral over v of f bar dv is called the volume integral over region v. So v is a region. So then this resulting integration is called volume integral. So briefly we denote the volume integral f bar r bar dv, or just we will write volume integral f dv over v, region v. So for Cartesian coordinates, we may write this volume integral as I bar triple integral over v f1 dx dy dz, j bar triple integral over v f2 dx dy dz, plus k bar triple integral f3 dx dy dz. So again, there is one illustrated example for volume integral. Evaluate the volume integral 2x plus y dv, where v is the closed region bounded by the cylinder. It is given by z equal to 4 minus x square at the plane, x equal to 0, y equal to 0, then yeah, x equal to 0, y equal to 0, y equal to 2, and z equal to 0. So the given cylinder, that is z equal to 4 minus x square, meets the x axis at y equal to 0, z equal to 0, at x square equal to 4, or x equal to 2. Yeah. So that is at the point 2, 0, 0. So if you put y equal to 0 here, so it will imply x square equal to 4, or that will imply x equal to 2. So if you put y equal to 0, because this cylinder meets x axis at y equal to 0, z equal to 0. And if you put y equal to 0 in the equation of cylinder, you will get x square equal to 4, or you will get x equal to 2. So that is at the point 2, 0, 0. So this cylinder meets x axis at point 2, 0, 0. So you can write cylinder meets x-axis at point 2, 0, 0. So it meets z-axis at z equal to 4. That is at 0, 0, 4. Yeah, naturally it meets z-axis at z equal to 4. And on z-axis, x, y coordinates will be 0. So naturally it will meet at 0, 0, 4 to z-axis. So therefore the limit of integration are as under. So z equal to 4 to z equal to 4 minus x square. These are the limits of z. Y equal to 0 to y equal to 2. These are given already. It is given. Yeah, y equal to 0 to y equal to 2. These are the limits of y, and the limits of x are already, we are given x equal to 0 and x equal to 2. So it meets x axis at 2 0 0. So therefore x varies from 0 to 2. And also dv, that is dx, dy, dz. So let us put all these values in this volume integral. So volume integral over v 2 into 2x plus y dv will be, so this triple integral 2x plus y dx dy dz. So here we'll put the limits of x, then y, and then z, and we'll evaluate this triple integral. So you'll get yeah. So first evaluate the integral with respect to z. So here you get the integral of dz, that is z, and limits are from 4 to 4 minus x square. So it will be 4 minus x square minus 4. It will be just minus x square. Minus you can take outside of this integration, and then again integrate with respect to y. So you'll get x square to x plus y dy. So x square will be outside of integration, or you can multiply it by x square. So it will be 2x cube plus x square y. So 2x cube dy. So its integration will be, so 2x cube will be outside of integration and just integration of y, and you are putting limits of y, that is from 0 to 2. So it will be, and again integration of x square y, that is x square y square upon 2. So after putting limits you will get, and it has 4x cube plus 2x square, and lastly you will integrate with respect to x. So limits are from 0 to 2, and its integration will be 4x4 divided by 4 plus 2x cube divided by 3, limits from 0 to 2. So after simplification you will get its value, that is minus 64 divided by 3. So this is the end of this topic, that is line integral, surface integral, and volume integral. So in next lectures, we'll see uh, some theorems on transformation of a line integral to volume integral, or surface integral to volume integral, or volume integral to a line integral. So I will stop here.